So in section 8.3, we're going to work on hypothesis tests for a population mean, which is our mu here. Now, there's a couple different types of tests depending on what you know. So the first case assumes that you know what the population standard deviation is. This feels totally unrealistic because it's unlikely that you wouldn't know what the mean is, but somehow you know the standard deviation. Now, if you do know the standard deviation for some reason and not the mean, then you end up doing a test based on a z-test, the z-distribution, which is your standard normal distribution. There's a couple different ways you can do your hypothesis test. One is to set up your critical regions like this so that when you calculate a test statistic, that's your z calculation over here. When you set up that test statistic and calculate it, if it falls in the shaded region, then you reject H0. There's nothing wrong with that, but I like the flexibility of working with a p-value instead. So that's going to be our approach here. And it's going to make our life a lot simpler because we won't have to look up critical values from the z-distribution, etc. So on your handout where it says do this or that, I think I've set this up so we're going to be geared towards doing the first part of this. It is find the p-value, reject the null hypothesis if the p-value is less than alpha, and then state your conclusion in words. So that's what we're going to be end up doing for these types of hypotheses. Now, if you don't know what sigma is, which seems more likely, then the work's going to be pretty much the same, except that it changes the distribution. Instead of a z distribution like we just had, we're going to work with a t distribution. You still set up your critical regions, etc., but this time you're going to be looking for those critical regions from the t tables or from some software that tells you about the distribution of your student t. Now, to kind of get started and to refresh things, let's go to this one right here. And it'll also help us practice writing our conclusions, or excuse me, setting up our null and alternative hypothesis. So our goal is to use technology to find the p-value for the hypothesis test described below. So the claim is that the smartphone carrier's data speeds at airport has a mean of 16 megabits per second. Sample size is 24, and the test statistic is 2.03. So there's a couple things we got to do here first. And the first thing we got to do is we got to write down our null and alternative hypothesis. So let's do that. Now, the original claim here is that mu equals 16. Is that original claim going to be part of the null or alternative hypothesis?
No.
Going to be part of the null hypothesis. Good job, because it contains the possibility of equality. What about the alternative hypothesis? What has to be true there?
Mu is not equal to 16.
Mu is not equal to 16. Yeah, nice. So with that, we can look at the alternative hypothesis. It tells us how many tails for our test. So let's do that. What kind of a tail test is this going to be? A left tail, a right tail, or a two-tail?
Two-tail. Two-tail.
Good, a two-tail. And let's go back here. We had some other things we could take down. N is 24 and T is 2.013. So with that information, we're going to go to StatDisk. And let me just kind of quickly swing down here. What we're looking for is the area to the right of 2.03 or to the left of negative 2.03. So That's what the p-value is going to consist of, is that area. So go to StatDisk. In StatDisk, you want to go to Analysis, and then Probability Distributions, and then Student T Distribution. So I'll write that down here. You're going to go to Analysis, then Probability Distribution, and then Student T. And it's going to help us find the correct area. So let me get back there. Come on. There we go. Now they're asking for the degrees of freedom. Is that the same thing as n?
No, it's n minus 1. Right?
Excellent. So if n is 24, our degrees of freedom is 23. So yeah, you have to put in your degrees of freedom, not n. So you got to be careful there. Let's put that at 23. The t-value we got was 2.013. Now there's a lot of stuff here, but which one's going to be our p-value out of all this?
Is it going to be the two-tailed one?
Yeah, thanks, Tahisha. It's going to be the two-tailed one. So two-tailed one is going to be 0.055964, et cetera. All right, probably good enough just to do 4 digits. I don't know, I just copied down all of them. But there's your p-value. Nice. And what that represents is the area in that distribution in the two tails. So if you were to draw it, let me just draw a quick distribution here. And you might notice that all my all my z and t distributions kind of look the same. What you're getting is the area in both tails. So here and here, degrees of freedom equals 23. Getting that area out here. Now, if we look, we should see that the area, say to the right of 2.03 should be half of what we just had. So let's look back here at our distribution, the area to the right. Yeah, about 0.0279, et cetera. Sounds about right. Or the area to the left of that negative. Well, let's see, the area to the left of that is just going to be 1 minus the area to the right of that. And you can see that by looking at those first two values of the cumulative probabilities. All right, so that's our p-value. Nice. Are we okay with that one?
Yes.
Thank you. Now, I think there was another one there, so let's practice that, and then we'll move on to some more things with our t-distributions and testing the hypothesis mean. Second one says, the claim that the 12 a.m. body temperatures has a mean which is less than 98.6. Okay, so let's take a look at that. So I got to claim that the mean is less than 98.6, n equals 6, and t equals negative 1.924. So those are the things that I want to write down. This is still example C on your handout. Is this part of the null or alternative hypothesis?
Alternative.
It's part of the alternative, so mu is less than 98.6. What should I write here for the null hypothesis?
Mu is greater than or equal to 98.6.
Perfect. Mu is greater than or equal to 98.6. So, all right. Now keep in mind that my math lab will probably just regard this as mu equals 98.6. Excuse me. I like doing this. I think it's a little bit more user-friendly for you. And this is what I'll accept on a test. I mean, I'll accept either one, to be honest. So, but just so you know, that's probably what my math lab is going to expect. Now, what tail test is this one? Left tail, right tail, or two tail?
Right tail.
Left tail.
Left tail.
All right, so it's a 2-to-1 vote right now. How about one more to Kiss? Which one?
Left tail.
Left tail, good. So when the parameter is on the left side like this, the inequality points in the direction of the tail. So that's a left tail test. So what you're looking for then is really the area to the left of that value. So there we go. So our p-value in this case is really going to be the area in the left tail here. So this little piece. So again, we're going to go look that up in StatDisk. How many degrees of freedom do I have this time?
5.
5.
Yes, 5. Again, n minus 1. The t-statistic was negative 1.924. And I want the area to the left of that. Okay. Bigger than I might have guessed, but, you know, still reasonable. 0.0562, we'll call it. Rounding it off to the 4th digit. Nice. Okay, so are we comfortable with the p-values? And it's also been a good review of setting up our null and alternative hypothesis here. Let's actually do some examples that require us to do the actual whole hypothesis test. Now, the good news for us is that, typically speaking, we won't have to find the p-values. That'll be provided to us by the output from StatDisk. We'll just use the p-value to decide if we're going to accept our null hypothesis or reject it. Now, just as a reminder, in terms of deciding whether or not you're going to accept or reject, we had 2 little sayings. If p is low, can anyone finish that?
HO must
Gotta
go.
go.
HO must go. And basically what that means is if your p-value is less than alpha, then you want to reject the null hypothesis. Reject H0. What was the other one? If p is high,
HO must fly.
HO must fly. And basically what that means, if the p-value is greater than alpha, then fail to reject HO. So it gives you a nice little decision process there. I don't think I've ever seen the p-value actually equal alpha except in a contrived situation with the book. But at that point, you're, you know, in my mind, you're free to do what you want. And if you publish the p-value, then people can make their own decision, which is something that they should do. When you read journal articles, you'll see that quite often. They'll put the p-value in there so that you can make your own subjective decision. Okay, So let's do some actual problems then. And I think we'll start with, we'll start by looking at these two cases. This one is just not going to happen. If for some reason you are given the standard deviation, we can take care of that in the software. But let's look at the requirements for a hypothesis test in the case where you're testing for a hypothesis mean, or testing a hypothesis regarding a population mean, and we don't know what sigma is. Now, there's some assumptions. Sigma is unknown. All right, so we got that. The population is normally distributed, or n is greater than 30. So one of these two has to be true. All right, cool. Well, I think that's the point of the first example. Maybe we should just take a quick look at this one. So example A, which one of the following is not a requirement for testing a claim about a population mean with sigma not known? And unfortunately, I think maybe on your handout, maybe I should have looked at it here. No, I didn't. I forgot to cross that out, but so the requirement that we don't need to worry about in this one, that's not really part of a test like this, is that the mean is equal to 1. No, but we need to have that it's normally distributed with a sample size greater than 30, don't know the standard deviation, and then we have a simple random sample. So all three of those are going to be requirements. Now, let's move down to example B. 12 different video games showing violence were observed. The duration times of violence were recorded with times in seconds listed below. What requirements must be satisfied to test a claim that the sample is from a population with a mean greater than 75 seconds? Are the requirements satisfied? Well, let's take a look at this. How many samples do we have here? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 samples. So we certainly don't have n is greater than 30. So that's not so good. But that's not the only possibility. N can be greater than 30, or you can have a population which is normally distributed. So we should check that. The observations from a simple random sample, okay, that's something that we can't really cover too well. Conditions for a binomial distribution must be satisfied. No, that one's not true. That would apply to our work from section 8.1. What about this one? At least one observation must be above or below 75 seconds. Does that sound like one of our requirements?
No.
No, that's not. So the requirements that we need to check are these two. And to that end, let's check and see if if this looks like it's from a normal distribution. So I'll tell you what, somebody read those for me while I put them into StatDisk, and then once I get them into StatDisk, I'll share with you all the data through the chat. So can somebody read those values to me?
83,
83, good.
13, 605, 52, 0, 58, 200, 221.
221.
Yep. 46. 166 is number 9.
166 is the number, okay.
Yep. And then 0,
And then 0, good.
2, and then 58.
Awesome, thank you. So
You're
let me
welcome.
copy that. And then paste it in the chat for you guys. Thank you so much, that was helpful. There you go. So you should be able to input the data. Okay. So we need to decide if this comes from a normal distribution. Now, typically speaking, I'm not going to slow down too much to test these things formally. Not all the time, because we just can't. We'd never get through any examples, or hardly any examples if we did. But it's for an intro example, let's do it. Where can we go to see if this is a normal distribution? Does anyone remember that?
Analysis and then normal distribution?
Close.
Or confidence or assessing. I forget. I don't know. It's like assessing.
You have to do like a histogram or normal quantile plot after you go
Yeah,
to data.
you could. Yeah, both of those. Excellent. Now, what I'll do it all in once is to go to data and then normality assessment, and that'll give us everything. So in status, you go to data and then normality assessment. Okay, so like this. And let's see what happens when we go there. Let's see, try it again. Data, normality assessment. Ask me what column. Well, I only got one column of data, so that kind of narrows things down. And what I like about normality assessment is it gives me everything. So, in fact, we can appreciate some of this a little bit more. Let's just start with the most basic one, the histogram. Does that look like a normal distribution?
No.
No, not at all. How about the normal quantile plot? Does that look any better? No, it's not. And in fact, if you really want to put the nail in the coffin, you can appreciate this now. Reject normality with a 0.05 significance level, reject normality with a 0.01 significance level. Basically, the data have proved themselves beyond a shadow of a doubt that they're not from a normal distribution. They're just not. So if you're asked to be doing a test with this data, you really shouldn't be using the current test. So is other requirement satisfied? All right. We don't have to worry about the binomial distribution. It's not a normal distribution. I'd say C is looking pretty good. Wait. Oh, okay. Yeah, that one's looking. C is looking pretty good so far. Well, the requirements certainly aren't satisfied, so it's not any of these. And yeah, C is looking pretty good. Kind of a process of elimination. Because it's certainly nothing that says yes. So it has to be something that says no. And C fits the bill. Our sample size was 12. Sample data is not normally distributed. And there's no way to know if this was a simple random sample. So basically it fails. Okay, so we've danced around enough that it's time to actually do a full example. So let's flip over to example D here. Okay. So park officials make prediction times of the next eruption of a particular geyser. Psst. To give you a clue, geyser is Old Faithful, and collect data for errors in minutes in those predictions. The display from technology available below results from using prediction errors to test the claim that the mean prediction error is equal to 0. Comment on the accuracy of predictions, use a 5% significance level, identify the null alternative hypothesis, p-value, etc. So they're actually going to give you some information here. So we'll do kind of like part of a statistic, or part of the work here. So let's look back here at the example, the claim. The mean prediction error is equal to 0. All right. Can anyone frame that in terms of some symbols? What are right there? Mean prediction.
Mu equals 0.
Perfect. Mu equals 0. Thank you, Jada. So mu equals 0, is that going to be part of our null or alternative hypothesis?
No.
The null hypothesis. Mu equals 0. Mu not equal 0 is going to be our alternative. So that's typically our step 1, is establish the null and alternative hypothesis. Step 2 is to decide on alpha. And they told us right there that alpha is 0.05. Now, if they don't tell you what alpha is, either choose 0.05 or 0.01, as you see fit. And of course, your choice on that might be influenced by, what happens if you make a type 1 error. If it's really important that you not screw up in a type 1 way, then choose alpha as 0.01 or maybe even less. Okay, let's look back at our handout, our little guide. Step 1, step 2, input your data. Okay, well, we're not going to be able to do that because this one doesn't really give us any data. So step 3 is not applicable. But you input your data to get the p-value, and at least they did tell us the p-value. So let's take note of that. The p-value in this one was 0. There we go, right there. P-value is 0. P-value equals 0. So that brings us to step 5. Step 5, we got to decide what we think about the null or alternative hypothesis. Which one's going to end up being our conclusion? Well, what you want to do is compare the p-value to alpha. P-value was 0, and alpha was 0.05. What kind of inequality am I going to put here?
0.000 is less than 0.05. So
awesome. Thank you, Shane. It's less than. So at the start of this section, I talked about, what to do with your p-value and the decisions to make. That was back here. What are we going to do with our null hypothesis?
We're going to reject it.
Yeah, our p-value is less than alpha. Reject H naught. If the p-value is low, H naught must go. So that's step 5, is to reject H naught. And then step 6, we want to state our conclusion in words. So for that, I gave you a little bit of a handout last time. Let me see if I can't find that for us real quick. Yeah, here we go. So this is what we're going to use to word the conclusions from our hypothesis. Does the original claim contain the condition of equality? Well, let's look back here. Our original claim was this one right here. Yeah, that looks like it contains the condition of equality. Okay, that's fine. So that puts us here on our path. Do you reject H naught? Yes. So of these four statements, we want to work with A and basically just copy down all of what's there until we get to the point where we say that and dot, dot, dot. Then you have to describe that original claim in words. So there is sufficient evidence to warrant rejection of the claim and all I'm doing is I'm copying down exactly what's there. That. So there's sufficient evidence to warrant rejection of the claim that the mean error of prediction times is 0. Okay. Now, be careful with the second part. Please don't use symbols. And please talk about what it is that you're testing in words. Just don't end with mu equals 0. All right. The idea here is you can communicate your findings to somebody who maybe hasn't had a stat class, so they can say, oh, okay, on average they're not getting it right. Because if the mean prediction error was 0, that means sometimes they're below, sometimes they're above, but on average they're getting it right. That's not what's going on with the prediction times for Old Faithful. They're not getting it right on average. Now, where they're landing, we'd actually need the data to say. But there we go for that one.
Real quick, sir.
Yes.
Could you please go over step 3 and 4 again? I kind of missed that part.
Sure. So step 3 for us is typically going to be to input the data or input some summary statistics into StatDisk. But since we didn't have the data, that one was not applicable. We didn't do that part. But the output of the problem did show us what the p-value was. So let me get back there. And that's right down here in blue. The p-value was 0.00. So they told us the p-value. So that's what I wrote down for step 4 was the p-value.
Okay, thank you.
So the p-value, and once you have the p-value, you're able to do step 5. All right. Other questions on this one?
I have a question. How did you get the p-value is 0?
It came from the problem. But in our next example, we'll actually get it from our software. Typically, that's where you're going to get your p-value is from the software.
Okay.
All right. Thank you. Anything else on this one? Okay. We're going to turn to the book to do one. And let's see. Come on. There we go. And I want to be on page 397. So let me just flip over a page. We're going to do problem number 16. So we'll scroll down a little bit. Now they actually give us some summary statistics, but just for practice and for giggles, we're gonna do this all ourselves. Data set 21, earthquakes. In Appendix B, lists earthquake depths and summary statistics are n equals 600, x bar equals all this, blah, blah, blah. Use the 0.01 significance level to test the claim of a seismologist that these earthquakes are from a population with a mean equal to 5 kilometers. So, okay.
What page is this again? Oh,
Page
397.
397.
Okay.
Okay. So let's start with this part. Want to test the claim of a seismologist that these earthquakes are from a population with a mean equal to 5 kilometers. So that's your original claim. This is problem 16, page 397. Equals 5 kilometers, 3.1 miles. That's our original claim. I'm taking note of this because eventually I'm going to need to phrase my conclusion, and it's helpful to know the original claim at that point. So step one, we're going to set up our null and alternative hypothesis, HO and HA. HO is that mu equals 5 kilometers. HA is that it's not equal to 5 kilometers. Okay. Now we should also be paying attention to the assumptions. Again, I'm not going to slow down to look at those, but I think our sample size is going to be large enough that we're not going to have to worry about the normal distribution part, because I think we'll have more than 30 observations. Step two is alpha. What's alpha in this case?
0.01.
Yeah, 0.01. In case you're wondering where she got that, it's right here. Use a 1% significance level. Step three, this is where we get our data into StatDisk. So let's go to StatDisk. If you want, you can clear out the data that we have there. I don't think it'll matter, because I think it'll be overwritten. Let's find out. So in StatDisk, you're going to go to Data Sets, and then 13th edition, and then scroll all the way down to Data Set 21. Data, 13th edition, and then Data Set 21, earthquakes. All right, so let me do that. And bam, it puts everything in there for us, which is wonderful. And our sample size is certainly greater than 30. So at least we've satisfied some of our assumptions. We can't really talk about the simple random sample part, but we'll deal with that. Has everyone got the data in?
Yes.
Thanks, Joe.
Yeah.
Okay, good. Now it's time for some analysis. This is where we're going to figure out our p-value. So go to analysis. And which menu do you think I want to choose down here?
Would be hypothesis testing.
Yeah, the hypothesis testing. So hypothesis testing. Now you've got several different choices for a mean, but we've only got one sample of data. These are for some other things. That'll be chapter 9 stuff. So we want mean one sample. So StatDisk, it's going to be analysis. And then hypothesis testing. And then mean one sample. So I'm writing those down here so that if you chance to look at the notes, then you can figure out the commands.
Thank you.
So let's see, analysis, hypothesis testing, mean one sample. Okay, so the first thing we need to do is we need to look at our alternative hypothesis. You've got three choices. Is the alternative hypothesis mu is not equal to something, mu is greater than something, or mu is less than something? 1, 2, or 3. Which one should I choose?
One.
I'm thinking 1 looks good. Our significance level was 0.01. Ooh. You know what though? Before I get too far on this, let me go up here and click use data, because we actually have the data here. And yeah, so click use data and it reset my significance level, which is unfortunate. Claimed mean. Well, the claimed mean was 5. That comes from your hypothesis. That's the claimed mean. It's this part right here that is going to help you decide if you're using a t-test or a z-test. So you really don't see it too much. But if you put in a value for sigma, then you'd be using a z-test. For the most part, you're going to leave that blank. And I like that the software here puts if known to make you feel a little bit more at ease, leaving it blank. Which column should I use, magnitude or depth?
Magnitude.
I think it's talking about earthquake depth.
Yeah.
Yeah, so choose that. Now, what am I looking for? We got all this nice output here. It gives me a t-statistic, gives me a critical t, gives me a confidence interval. What am I looking for?
The p-value?
Yeah, the p-value. What's our p-value after all that? P-value was 0.00005. Awesome. So your p-value, in case you're not seeing it, is down here. So a lot of work to get that one little one little wonderful number. And that brings us to step 5. What's that p-value tell us about our null hypothesis? Somebody I haven't heard from this morning yet. What are we going to get there? Just to remind you, here's our decisions. Here's our possible decisions.
So are you going to put that p-value is less than sigma? And so we reject it?
So our p-value was 0.00005 and alpha was 0.01. So yeah, p-value is less than that. So therefore, which is these little triangle of dots, therefore reject H0. Yeah, get rid of it. We've got conclusive evidence to suggest that the null hypothesis is false. Awesome. So let's go to step 6 and figure out what the conclusion is going to be. So you might want to pull up that handout again. So here it is right here. Try and figure out which one of these, and I've labeled them A, B, C, or D, which one of them is what you're going to use to help frame your conclusion. And Chloe, you're out there this morning? All right. Caitlin, can you help us out? Which one do you think we're going to use?
Oh, I'm not sure.
Okay, we'll tell you what, let's work it together. Our original claim was this one right here. Mu equals 5 kilometers. So that's the original claim. And let's look back at our little decision matrix here, or decision tree. Does the original claim contain the condition of equality? Which branch should I take?
Yes.
Yes.
Yes. So we'll go here. Did we reject H naught?
Yes.
Yes.
Yes. So that brings us to here, A. So we're going to use A to write down our conclusion. There is sufficient evidence to warrant rejection of the claim that, so let me just copy that down here in my notes. There is sufficient evidence to warrant rejection of the claim now. All that's just copying things down. Where you earn the points on this is not only by choosing the right one of those four, but also by stating our null hypothesis in words, or our original claim in words. What would be some good words for this?
I tried that there is significant evidence to warrant rejection of the claim that these earthquakes are from a population with a mean of 5 kilometers. Does that work?
Wow, that's great. Yeah, that's
Thank
even
you.
better than what I'm
Copied
going to
it
write.
from the book.
I was just going to write there's sufficient evidence to warrant rejection of the claim that the mean depth of earthquakes is 5 kilometers. Yay. So yours is actually a little bit better than this, but this is good enough for what we need here. All right. How's that one looking? We okay on that one?
Yes.
Thank you. Now, below here in the output from StatDisk, they actually had a confidence interval. So here's your 99% confidence interval. So they actually took the data and said, all right, let's build a confidence interval around this. Do you think that this confidence interval should contain 5 or no? What would you think? Should your confidence interval contain mu equals 5?
Yes.
Okay, so we got a yes. Let's think of it though in light of our conclusion. Our conclusion, I appreciate your participation here. Our conclusion was not that mu equals 5 kilometers, but it was different than 5 kilometers, right? So if we constructed a confidence interval, should that confidence interval have 5 as one of the possibilities?
No.
If we rejected H naught, we're saying this isn't true. And our confidence interval probably shouldn't contain that. So our confidence interval goes from 5.3 is less than mu is less than 6.3. And that makes sense because this is saying that mu is probably different than 5 because 5 is not in this interval, but that matches our conclusion. In fact, some people conduct their hypothesis test really by constructing a confidence interval. So it's a different way of doing this. We're doing it with a p-value approach, whereas if our p-value is less than alpha, then you reject. If it's greater than alpha, you fail to reject. So if we fail to reject, then we should have gotten a confidence interval that would have 5 as one of the possibilities. That would go along with the decision not to reject. Okay. Anything else on that one? I think we wrapped that one up pretty good. All right, I'm going to split this into 2 parts, our recording here, so we'll end part 1 right here.